Okay, let's continue with the concept of a derivative at a point, or an instantaneous rate of change at a single point. So last time we defined the derivative of a function f at a point where x is equal to a is the gradient or slope of the tangent line to that curve at x equal a, and it represents the instantaneous rate of change of the function at that point. And so we started to calculate that, and we learned by doing the limit of the difference quotient, we were able to find the derivative. So let's practice a few examples. Using first principles. Now, what do I mean by that? Well, that means we're going to use the limit as h approaches 0 of f of a plus h minus f of a all over h. And that's going to be the derivative at the point A. Derivative of f at x equal a. And the shorthand notation for that is f prime of a, with a little tick mark, f prime of a. So those are the different representations for a derivative. All right, so let's do that for this specific point. So we're going to find the limit, and that's what they mean by first principles. We're using this limit of the difference quotient. Limit as h approaches 0. Now, I'll go ahead and write out a little more formally. So we're going to do f of a plus h. Now, a in this case is -1. So -1 plus h minus f of a, so f of -1, all over h. You might want to hit pause and try and calculate this yourself and then see how you did. Okay, so we're doing the limit as h approaches 0. Now, I'm taking -1 plus h and I'm plugging it into the f function wherever I see x. So namely in the denominator there. So this is going to be 1 over, I'll put it in parentheses, -1 plus h plus 2 minus f of -1, that's 1 over -1. Oh, that's terrible. -1 plus 2, that's terrible again. Doesn't like me. -1 plus 2, all over h. Okay, so what we're calculating here is f prime of -1. The derivative of f at x equals -1. So we keep going. And it's actually sloppy to not write the limit statement, but sometimes people will over on the side do their calculations for simplifying the difference quotient, and then they'll plug it back in. So I'm just going to keep going forward so it's easier to follow. All right, so first let's simplify these fractions in the numerator. So I'm going to have 1 over 1 plus h, and then minus 1 over 1, which is just 1, all over h. Now this is a complex fraction. So in order to deal with this, I need to combine, let's circle it in a different color. I need to combine these terms by having a common denominator. So we're going to be doing the limit as h approaches 0 of all this after we simplify. So we have 1 over 1 plus h minus 1 plus h over 1 plus h, all over h. Now I can combine those two fractions because they have the same denominator, and I'll subtract the numerators, and I'm going to be left with 1 minus the quantity 1 plus h. And by the way, be careful with this. We have to distribute that negative, so it's actually going to simplify to just a negative h. That's a common mistake. Let's take this and continue it right up here. Equals limit as h approaches 0 of negative h over 1 plus h all over h. Now, dividing by h is the same as multiplying by its reciprocal, 1 over h. So I can change this to the opposite of h over 1 plus h times 1 over h. Now I can do some canceling. That reduces to 1 and negative 1. So I'm doing the limit as h approaches 0 of negative 1 over 1 plus h. Now I can actually evaluate this limit. I couldn't originally, because if I just plug in 0 for h back in the beginning, right here, I'm going to get it divide by 0. So I had to wait until I simplified my expression. And so now as h approaches 0, I'm going to get negative 1 over 1, which is just negative 1. So this is saying, let's take a look at this. Let's look at the graph of 1 over x plus 2, the quantity x plus 2, and just in the standard window. And I'm finding the derivative at x equals negative 1. And you can see that's the point on the graph. And if you drew a tangent line there at negative 1, second, draw tangent line at negative 1, does that have a slope of negative 1? And sure enough, you can see it shows it to you as y equal negative 1 point, and then a whole bunch of zeros, and then 1, x, plus, and then negative 1 times 10 to the negative 6th, which basically is 0. So the slope of that line is negative 1, and the y-intercept is 0. All right, well, why couldn't we do that right off the bat? Well, later on down the line, I can give you a problem that you won't be able to use your calculator to figure it out on. Calculator's not smart enough. All right, so let's look at another example. Write the equation of the tangent line to this curve at x equal 1. How is this question different than the last one? The last one said, using first principles, find the gradient of the tangent. Here I'm asking you to find the equation of the tangent line. So all we did in the last problem was find the slope of the tangent line. Here I actually want you to find the equation of the line. So we're going to need the slope, and we're going to need a point. So to find the slope, we need to find, if I call this, well, I call it y. So y prime of 1, that's going to be the slope, the derivative at 1. And then I need a point. And so my point is 1 comma something. And if I plug 1 into x, I'm going to get y is equal to 4. So the point on the graph is 1 comma 4. And now we have to calculate the derivative at 1. So let's do the derivative first. So that's going to be the limit as h approaches 0 of f of a plus h. So in this case, it's going to be 5 minus, and then x, I'm going to plug in a plus h, so 1 plus h squared. And then minus f of a, so f of 1, or y of 1, which is 4. Actually, I'll write this out. 5 minus 1 squared. So here, I'll put these in brackets, and you can see what I've evaluated there, and then all over h. So what that really did was I did f of a plus h minus f of a all over h. All right, so let's go ahead and simplify this to find the derivative, or the slope of the tangent line. And then once we have the slope of the tangent line and we use the point, we can get the equation of the tangent line. So when I simplify the first part, I'm going to have 5 minus, and I'm going to use parentheses, 1 plus h squared. That's 1 plus h times 1 plus h. So that'll give me 1 plus 2h plus h squared. And then, so that's in this bracket, minus, in the other bracket, 5 minus 1 is 4, all over h. I still can't evaluate the limit because that would be a divide by 0. So limit as h approaches 0. Now I can simplify the top, and I have a 5 minus 1 is 4, but that'll cancel with the minus 4 at the end. So I'm actually going to have a negative 2h minus h squared all over h. And then I can factor that. I'll keep going this way. So I'm going to have the limit as h approaches 0. And if I factor an h out of the top, I can cancel with the h on the bottom, and so I'll be left with negative 2. That's kind of sloppy. Negative 2 minus h. And that limit, if I plug in 0 for h, I get negative 2. So that's the slope of my tangent line. So I'm going to use that. And I need a point, so I'll use that. And now I can write my answer, and I'm just going to write it in point-slope form. So y minus 4 equals my derivative, negative 2, which is my slope, times x minus 1. And you're going to find in calculus, a lot of times it's better to leave it in point-slope form instead of slope-intercept form, for example, because by looking at this, right away you know what the derivative is. It's the slope right there. And you know we're doing the tangent line at the point. We have the point here, 1, 4. So leaving it in that form, it tells you a little bit more about what we're doing. So just to give you a visual for this, and I'm not even going to use the calculator on this one, I can graph 5 minus x squared. That's the same as negative x squared plus 5. So that's a parabola that opens downward, and it's been shifted up 5 units. So it's going to look something like this. And we were finding the tangent line at 1. So that's going to be right about here. And so that should be our equation, y minus 4 equals negative 2 times x minus 1. If I rearrange this into slope-intercept form, you're going to get, I'm going to write equals. That would be the same as y equals negative 2x, and then we'd have plus 2 plus 6. And sure enough, that looks about, and that was just a quick drawing, that looks about right. Okay, so make sure you understand the difference between the first example and this example and what it's asking for. All right, let's try one more. Find the derivative of g of x equals the natural log of x at x equal 2. So in other words, g prime of 2. Now if you start to set this up, you'll say, oh, okay, g prime of 2 equals, and you're going to use first principles, which is the limit of the difference quotient. Limit as h approaches 0 of g of 2 plus h minus g of 2 all over h. And then you get the limit as h approaches 0. And I'm going to plug in 2 plus h, so it's going to be the natural log of 2 plus h minus the natural log of 2 all over h. Well, this isn't a polynomial function, so I can't manipulate it in a way that I could cancel the h's. So algebraically, we're kind of stuck. There's no way we can find this limit by doing some sort of simplifying or factoring and canceling. So then we're going to have to use our calculator. So what we could do for this limit is we could just punch in that as a function, the natural log of 2 plus h, 2 plus, I have to use x for h, and then minus the natural log of 2, which is just a number, close parentheses. Now notice that's my entire numerator, so I enclose that all in parentheses, and then divided by h, except I'm using x instead of h. And then if I hit graph, I'm trying to find this limit as h approaches 0, or in other words, as x approaches 0. And you can see it's undefined, obviously, because there's a hole in the graph at 0. But if I get really close, so let's see, how about 0.1? My y value is about 0.487, so let's say 0.49. How about 0.01? 0.498. How about 0.001? 0.499. It looks like it's going to be about a half, 0.5, 0.5. I could approach it from the other side of 0, negative 0.00001. And sure enough, a little bit more than 0.5. So I'm guessing that the answer to this is going to be 0.5. Now, that was a really important thing to understand what I just did. I looked at this entire thing as a function. I'm not talking about the natural log of x. I didn't say, oh, let's look at the graph of the natural log of x and find the slope of the tangent line at 2. Something like that. Okay. What I did was I looked at this difference quotient as a separate function, and I found the limit of that function as x approached 0, and I got 0.5. So that's one way to handle problems like this where you can't simplify anymore to figure out the limit without using a calculator. But if that's the case, and we're going to have to use a calculator anyway, then if, let's say, if g of x equals the natural log of x, and I want to find g prime of 2, then let me show you a shortcut on the calculator to finding derivatives. So all you have to do is put your function in, natural log of x, and to find the derivative at 2, if you're on the graph screen, you can go to second trace to get to the calculator menu. And sure enough, number 6 here, dy dx, that's another notation for the derivative. It means the derivative of y with respect to x. We're going to choose that, and it's on the current graph, and I have to type in the x value. Well, I wanted the derivative at 2, so I hit 2. And sure enough, dy dx is 0.500004. And so you can guess that, well, maybe the calculator is making a little bit of a mistake here. So it's got some rounding error, so it's probably just 0.5. And actually, later on we'll learn it is exactly 0.5. So that's the shortcut to finding derivatives. You put your function in y equal, you press second trace, you go down and choose number 6, and then you type in the x value, x equals a value, and there's your derivative. If you're doing it from the home screen, you can likewise do something kind of similar, except it's in the math menu. So you press the math key, and you go all the way down to number 8, and deriv. And if you have a newer operating system, it gives you this fancy notation. So d dx, and then you put your function in there, natural log of x. Or actually, I could have just put in y1 because it's in y1 already. And then at x equals 2, and there's that same answer. So 2 different ways to do it on the calculator, from the home screen or from the graph. And that's a shortcut, but you should know how to do it using the difference quotient like we did in the last few examples. Okay, the assignment is worksheet 2.